Hello, this is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. Today, lecture 23b, the chain rule, part B. This is a continuation of lecture 23a, in which we introduced the chain rule. You will recall that the chain rule is a derivative rule that tells us how to find the derivative of a composition. It has two versions. Version 1 states that the derivative of f of g of x is f prime of g of x times g prime of x. It's the derivative of the outside function with the inside function plugged into it, and then that whole thing times the derivative of the inside function. Version 2 says exactly the same thing in a different way. If y is equal to f of g of x, you can break that up as y equals f of u, where u equals g of x. And given that setup, the derivative dy dx is the product of the derivative dy du with the derivative du dx. As an example, let's find the derivative of y equals the square root of x to the fourth plus 7x cubed minus 4. You could also write this as that polynomial raised to the power of 1/2, if you so chose. You'll recognize that this function that we want to find the derivative of is a composition. It's a polynomial plugged into the square root function. So we can find the derivative, therefore, with the chain rule. And let's use version 2. In version 2, we could write this function as y equals u to the power of 1/2, where the u is the polynomial x to the fourth plus 7x cubed minus 4. So once we've broken it up that way, we can find the derivative we want, dy dx, as dy du times du dx. Let's work out these two derivatives separately. Dy du is the derivative of u to the 1/2. It's the derivative of this function. And by the power rule, that's 1/2 u to the power of minus 1/2. And then we're multiplying times du dx, which would be the derivative of u equals x to the fourth plus 7x cubed minus 4. And that's just 4x cubed plus 21x squared. And we're almost done. Remember that now we have to get this u back in terms of x. And remember that u was this polynomial of x. So we're going to insert that right there at the u. We get 1/2 the quantity x to the fourth plus 7x cubed minus 4, all to the power of negative 1/2, times 4x cubed plus 21x squared. And that's our derivative. There is a little cleanup work that you may want to do. You could bring this polynomial to the negative 1/2 power down to the bottom and convert that power to a positive power. And then maybe revert that power of 1/2 to a radical. And we get this function as our derivative. So there we go. We found a derivative of a function with version 2 of the chain rule. And you could also use version 1 here if you wanted to, and you can see that happening right here. You're plugging your inside function into the derivative of your outside function, and then multiplying by the derivative of the inside function. Here's another example, sort of along the same lines. Let's differentiate sine fifth of x. Now remember, that's y equals the expression sine of x to the power of 5. So that's a composition. It's the function sine being plugged into the x to the fifth function. We could write it as y equals u to the fifth, where u is the function sine. So in differentiating this, since it's a composition, we would use the chain rule. And as you can see, we're set up to use version 2 of the chain rule here. dy dx would be dy du times du dx. Now dy du would be the derivative of y equals u to the fifth. That's 5u to the fourth. Times du dx would be the derivative of times the derivative of sine of x, and that's cosine of x. Almost done. We need to replace this u with what it is in terms of x. And remember, u is sine of x. So we get 5 sine of x to the fourth times cosine of x. And that's our derivative. You could streamline that a little bit as 5 sine to the fourth x cosine x, but that's just cosmetic. What happened in this example is a pattern that's going to happen over and over and over again, and it deserves a special mention. What we've done here in this example, and also on the example in the previous page, is we've found the derivative of a function raised to a power. Let's make that its own example. Let's differentiate a function g of x to a power of, say, n. If we want to differentiate g of x to the power of n, you'll recognize that as a composition. It's the power of n function with g of x plugged into it. So we could use the chain rule, part 2, to find the derivative. Y is equal to u to the power of n, where u is equal to g of x. And dy dx, the derivative we're looking for, is dy du times du dx. dy du would be n, would be the derivative of y equals u to the n. That's n times u to the n minus 1. And then this du dx, that's the derivative of u equals g of x. Well, we don't have an explicit function for g of x. We're just going to have to write g prime of x. And we've almost got our answer. We just have to put in for u what it is in terms of x. Remember, u is equal to g of x. So we get as an answer n times g of x to the power of n minus 1 times g prime of x. So what we've done here is we've looked at a generic function to a generic power, g of x to the power of n, and we've figured out the derivative of that, dy dx, is n times g of x to the power of n minus 1 times g prime of x. That's essentially what happened right here. 5 g of x to the power of 4 times g prime of x. But now we've done it for any function g of x and any power n. And we can make this a rule. We're going to call this the generalized power rule. It's kind of like the power rule, but instead of x to the power of n, it's differentiating g of x to the power of n. What we've just figured out in this example is that the derivative of a function g of x to a power of n is n times the function g of x raised to the power of n minus 1 times g prime of x. This basic pattern here that's happening, this derivative of a function to a power, happens so frequently that we're making our own rule for it, a separate rule called the generalized power rule. You'll see this a lot. A function to the power of n, the generalized power rule tells you what the derivative is. So for example, let's differentiate the expression e to the x tangent x all to the power of 3. That has the form of a g of x to the power of 3, where g of x is the product e to the x tangent x. So we could use the generalized power rule for this. Here g of x is this function and n is 3. So according to this template for the generalized power rule, we're going to get 3 times our function g of x to the power of 3 minus 1, and then we have to multiply by g prime of x. Now here, g is e to the x tangent x. That's a product. So g prime of x, we're going to have to get that with the product rule. And using the product rule, we take the derivative of the first function, which is e to the x, times the second function, tangent x, plus the first function, e to the x, plus the derivative of the second function, secant squared x. And there's our derivative. We got it in one step using the generalized power rule. This is essentially a chain rule problem, but because we have the generalized power rule, which we got using the chain rule, it's almost as if we're not even using the chain rule here. It feels that way. We get it in just one step. There are other generalized rules. Here's another pattern that will happen very, very often. You'll have a function y equals e raised to the power of g of x. E raised to a power of g of x. And you'll want to find the derivative of that. Well, to find the derivative of e to the power of g of x, you'll recognize that as a composition. It's y equals e to the power of u, where u is the power g of x. So we've broken that up into two pieces. And to find the derivative, we use the chain rule, version 2. The derivative dy dx equals dy du times du dx. And dy du is the derivative of y equals e to the u, which is e to the u. And du dx is the derivative of u equals g of x. So that's g prime of x. Almost done. This u here is equal to g of x. So we get e to the power of g of x times g prime of x. So in summary, what we've just figured out is that the derivative of e to the power of g of x equals e to the power of g of x times g prime of x. We're going to make that a new rule. Let's call it the generalized exponential rule. You know that the derivative of e to the x equals e to the x. This is telling you what is the derivative of e to the power of g of x. It's not e to the power of g of x. It's e to the power of g of x times g prime of x. So this basic pattern of differentiating e to the power of a function occurs so often that we have our own rule for it, the generalized exponential rule. So for example, imagine we have the derivative of e to the power of x cubed plus secant x. That's e to the power of g of x, where our g of x is this function x cubed plus secant x. So it fits the template for the generalized exponential rule. It's the derivative of e to the power of g of x. So our answer is going to be e to the power of g of x times g prime of x. Now, e to the power of g of x would be e to the power of x cubed plus secant x, but then we have to multiply that by the derivative of x cubed plus secant x, which would be, let's see, the derivative of x cubed is 3x squared, and the derivative of secant x is secant x tangent x. So there we go. You got to remember to put that whole thing in parentheses because we're not just multiplying this times 3x squared and then adding secant x tangent x. It's e to this power times this whole expression. That's our g prime of x. So there's our answer. And notice that we got it in just one step with the generalized exponential rule. We actually have a generalized derivative rule for every one of our derivative rules for specific functions. Here's a list of the rules we have. We've got the power rule. The derivative of e to the x is e to the x. We have derivative rules for all 6 trig functions. If you apply the chain rule to these rules, you get the corresponding generalized rule. For example, we just worked out the generalized power rule. It told us that the derivative of g to the x to the power of n is n g to the x to the power of n minus 1 times g prime of x. And the generalized exponential rule, it's what happens to this rule for the derivative of e to the x when you insert a g of x in for x. The derivative of e to the g of x is e to the g of x times g prime of x. And we could continue with this. For the derivative of sine of x equals cosine of x, if you take the derivative of sine of g of x, we get a generalized rule, cosine of g of x times g prime of x. That's the derivative of sine, which is cosine, with g of x plugged into it, times g prime of x. So we're going to look at this as a new generalized rule for sine of a function. You have probably already in your practice working exercises started to think this way, that automatically when you see the derivative of sine of g of x, you instantly think chain rule, that's going to be cosine with g of x plugged into it times g prime of x. And that's good because it means you're thinking in a way that's leading you to these generalized rules anyway. Likewise, there's a rule that generalizes the derivative of tangent. Corresponding to this rule is the derivative of tangent of g of x equals secant squared g of x with g prime of x times g prime of x. This rule generalizes as d dx of secant of g of x equals the derivative of secant, which is secant times tangent, with g of x plugged into it, times g prime of x. Likewise, the derivative of cosine of x equals minus sine of x generalizes as the derivative of cosine of g of x equals negative sine, with g of x plugged into it, times g prime of x. The derivative of cotangent of g of x by the chain rule would be negative cosecant squared with g of x plugged into it times g prime of x. And then finally we get this last generalized rule. It's just the chain rule applied to a familiar rule here. So we have a bunch of new rules here that are really just old rules combined with the chain rule, these generalized rules. And you should work, of course, enough exercises that you get really good with working out these and they're second nature. We'll work out a few examples here. First of all, think about the derivative of 5 times e to the secant x. The first thing you could do here is recognize that 5 is a constant. It can come out of the derivative, so 5 times the derivative of e to the secant x. And the derivative of e to the secant x, that's e to the power of g of x. We could find this derivative with the generalized exponential rule, which says you take e to the secant x and then multiply that times the derivative of secant x, e to the g of x times g prime of x. And here the derivative of secant x is secant x times tangent x. So quick, we got it in 2 steps, and probably if you were working this yourself, I'll bet you would not even factor out the 5 here. You just go straight from here to there in 1 step. That's good. Here's another one. Y equals e to the power of minus x. And what we want to do here is find the derivative dy dx. This problem is simple enough that it might almost trip you up. It looks so much like e to the power of x that you might say, well, the answer is going to be e to the power of minus x. But let's be really careful. This is not e to the power of x. It's e to the power of negative x. That's a function of x right there. It's multiplying x times minus 1. That's x times minus 1. So we really have here e to the power of g of x, where g of x is the function g of x equals minus x. So we have to use the generalized exponential rule here. E to the power of g of x times g prime of x. So that's e to the power of minus x, and then times the derivative of minus x, which is minus 1. So we get here as an answer, our derivative is negative e to the power of negative x. So be careful there. Sometimes it's easy to slip up and you're working so fast, you just say the derivative is going to be e to the power of minus x. That's not quite right. You have to use the chain rule here, or the generalized exponential rule. Let's also find the second derivative of this function. That would be the derivative of minus e to the minus x. So first of all, we have a minus here. So let's put that minus out in front. And then we take the derivative of e to the minus x. Well, actually, that's exactly what we just took the derivative of here. We could recycle our work. E to the minus x times the derivative of minus x, which is minus 1. And then these two negatives cancel out, and we just get as an answer, the second derivative is e to the power of minus x. And that's kind of interesting because you'll notice that the second derivative, e to the power of minus x, it's equal to our function y to the x. So here's a function, e to the power of minus x, whose second derivative equals it. So its third derivative would be this, its fourth derivative would be that, fifth derivative, sixth derivative, and so on. It just bounces back and forth between those two functions. Derivative of cosecant pi times x. That's the derivative of cosecant of g of x, where g of x is pi times x. The chain rule or the generalized cosecant rule would say you take the derivative of cosecant, which is minus cosecant cotangent. You plug in your g of x. Pi x goes in two places. And then you multiply by the derivative of pi x, which is just pi. So there's our derivative. Here's one. The derivative of tangent to the power of 8, 3e to the x over x. Let's analyze what's going on here. This is the derivative of a function tangent 3e to the x over x, whole thing to the power of 8. So it's a function raised to the power of 8. So for this, we could use the chain rule or the generalized power rule. Either way, we should get the same answer. Let's think about that generalized power rule. This is a g of x to the power of 8. So the answer is going to be 8 times g of x to the power of 8 minus 1, 7. All of that times the derivative, g prime of x, which would be the derivative of this inside stuff, the derivative of tangent 3e to the x over x. So right here in this step, we just applied the generalized power rule. But we're not done yet because we have to take the derivative of tangent of 3e to the x over x. And this derivative that we have to take, notice that's a composition. It's tangent of a g of x. So we have to use the chain rule to find that derivative. So let's work this out. First of all, let's bring down the 8 times tangent 3e to the x over x to the power of 7. Just bring that down. Now we work out this derivative. So it's the derivative of a composition, so we have to take the derivative of the outside function, tangent, which is secant squared, plug in the inside function, which is 3 e to the x over x, and then we're going to have to multiply by the derivative of that inside function. The derivative of 3 e to the x over x, and this is a quotient, so this derivative will be got using the quotient rule. It's the top function, 3 e to the x, times the bottom function, x. I'm sorry, it's the derivative of the top function. The derivative of 3 e to the x is 3 e to the x, then times the bottom function, x, and then minus the top function, 3 e to the x, times the derivative of x, which is just times 1, all over x squared. So that's our derivative. We did this in several steps, but as you work exercises, I guarantee it, you're going to get to the point where you do a problem like this just in one step. It'll almost be automatic. In fact, it will be automatic. You'll just go from, you'll look at this and you go, oh, generalized power rule, and then the inside function is a composition, so I've got to use the chain rule, and you just look at from this, you go straight to that, and you just write it down. You'll get good at this fast. It just takes a little practice. Here's another problem. Let's take the derivative of x cubed plus x times the function cosine of x cubed over x squared minus 1. Looking at this, we are taking the derivative of a product, this polynomial times this function here, cosine of this fraction. That's a product. So we're going to have to start out here using the product rule for the derivative of that product. Now, the product rule says you take the derivative of your first function, the derivative of x cubed plus x, multiply it times your second function, plus your first function, x cubed plus x, times the derivative of your second function. So there's the product rule right there. And we're not done yet because we've still got to take the derivative. There are two derivatives we have to take. We've got to take those derivatives. Well, the derivative of x cubed plus x is 3x squared plus 1, and it's being multiplied by this second function, plus, then we have the x cubed plus x, bring that down, and now we have the derivative of cosine of the function x cubed over x squared minus 1. This is a composition. It's cosine of this function. So to find this derivative, we have to use the chain rule. We first differentiate the function cosine, which is negative sign. We plug in this inside function into that derivative right there. And then we have to multiply by the derivative of this inside function, x cubed over x squared minus 1. Now, that inside function is a quotient, so to find its derivative, we have to use the quotient rule. Derivative of top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. And there we go. That's our derivative. Maybe there's a little cleanup to do here. You could bring that minus out over here. And this fraction, it's going to simplify a little bit. All of this stuff boils down to, let's see, you got a 3x to the fourth and a minus 2x to the fourth. That's just an x to the fourth. And a 3x squared times a minus 1, that's a minus 3x squared. So this numerator simplifies a little bit. Bring the negative outside here, put it there. That's probably about as simple as we can get the answer. So we'll put that in a box, call it our answer. Next example. Let's differentiate y equals sine x cubed plus 2 all over 5x e to the x. We're looking for dy dx. This function is a quotient. It's one function divided by another function. So the first rule we'll have to apply is the quotient rule. In the quotient rule, you take the denominator, you put it on the bottom, and you square it. Then on the top, you have the derivative of your top function here times your bottom function, 5x e to the x, minus the top function times the derivative of the bottom function. So in this step, we just applied the quotient rule, but we're not done yet, of course, because there are two derivatives to work out, this one and that one. So let's do that. The derivative of sine x cubed plus 2 would be, well, let's see. Sine of x cubed, that's a composition, so we got to use a chain rule there. That would be cosine with x cubed plugged into it times the derivative of x cubed plus the derivative of 2 is plus 0, and we're multiplying times the 5x e to the x. Then we have minus this top function, and now the derivative of 5x e to the x. 5x e to the x is a product. It's the function 5 times x times the function e to the x. So to find this derivative, we have to use the product rule. We would take the derivative of the first function, the derivative of 5x is 5, multiply it times the second function, and then take the first function, 5x, times the derivative of the second function. And the derivative of e to the x is e to the x. So here we go. That's an answer, but you could probably simplify this a good bit. We could knock out this 0, for instance. Let's clean this up. On the bottom, we have 5x e to the x times itself. And this term here would be 5x e to the x times cosine x cubed 3x squared. Let's consolidate that. You got some x terms that multiply. X times x squared is x cubed. You got a 3 there. You've got a cosine of x cubed. And that 5 e to the x is right there. And then we have minus the sine x cubed plus 2 times our expression here. And looking at this expression, this derivative of 5x e to the x, looks like we could factor out a 5 e to the x from that. So let's do so. That's 5 e to the x times 1 plus x. And let's take stock of what we have here. Notice that in the two terms on the top, we have a 5 e to the x, and we also have a 5 e to the x on the bottom. So there's a little bit of cancellation we could do if we so chose. We could factor a 5 e to the x out of the top, and we get this, 5 e to the x times all of that. And on the bottom, let's factor a 5 e to the x out of all of this. And now the 5 e to the x's cancel. And we get a slight simplification. Here's our answer. So you'll notice in this problem that we started out with the quotient rule, and we had to use all kinds of other derivative rules, including, of course, the chain rule. And that's typical. So in summary, in these past two lectures, we have introduced the all-important chain rule that greatly expands the kinds of functions we can find derivatives of. Please get some practice with this, because we're going to build on it. Coming up in lecture 24, Our purpose will be to come up with some new rules. First of all, we're going to find the derivative of an inverse function. And this will be very useful because since ln of x is the inverse of e to the x, we'll then be able to come up with the derivative rule for ln of x, which we don't have yet. Then the derivative of the function log base a of x. And then one gap that we have is we don't yet have the derivative of a to the power of x. Sure, the derivative of e to the power of x equals e to the power of x, but what about something like 2 to the power of x? We're lacking a rule for that. So in lecture 24, we'll have 4 new rules. So that's it for today. I hope to see you in lecture 24. Goodbye.